So today we are going to continue with the space-based analysis. And
can you share the screen?
Absolutely. And I guess, right?
Yes. Yep.
Okay. So IT may come to my office today for some small rearrangements. So if there would be interruption for a few minutes, I'm sorry for this, but it's out of my control.
No worries.
But it should be very short. Okay. So just started analysis before the meeting. So let me share it. Okay. So you can see right now the tool running analysis with the SpiceNet list. So what's actually the difference between the run that you have seen yesterday and the run that I run right now? So let me show you two scripts. So we have previous file. This is flow prime that I explained to you yesterday. The flow that I run now, this is flow static. So let me show you the difference. So I use TCAD for this. Nice tool. So what we have in a view command read SpiceNet list. So I don't know. Can you see my cursor moving? So this is new command read SpiceNet list. So now we read in actual electric circuit. The difference is that we do some spice settings, and in this run we run not only airdrop, but we run also power, thermal analysis. So this we have like additional settings for power and thermal. These settings were done by Michelle, and I do not know how really how correct these theta J settings are. This one is pretty generic. These are just default settings. As you can see, voltage source assignment is all the same. And what we are missing here, we are missing in this script for analog run, we are missing all these set CS commands that you can see on the left. Because now all the current sources are taken from SPICE simulation. In DF we have locations of the devices. If you take a look at simulation net list, this one. See, instrument original SpiceNet list, and you can see we have quite a lot of probe statements that we request transient power, and that's quite a annotation. Power, also currents. If you scroll down, it's really big. It's now like megabytes versus just less than 1 kilobytes original net list. So we add more annotation to query this data from SPICE for electrical engine simulation. Okay, so difference is really minimal, and major differences that we include command read SpiceNet list. Also in flow prime, this command create net. So you see we created 6 nets at once. when you run spice-based analysis, you do not need to do this because these nets are automatically recognized from voltage sources. So you do not need to create nets explicitly. What codes you have in SpiceNet list, tool knows about their existence.
Alex, I have a question on that. The static TCL. Can you go back?
Yeah. Let's see. Okay. Yes.
I think if you scroll down to where the substrate thickness definition, so it says 200 micron.
Yes, for microns.
Our device should be maybe 650.
See, it's not a problem. You see, 200 we use it excuse, by default for smaller blocks. You can set it to 650. From my experience, bulk substrate volume, especially combined with the package resistance, it doesn't have much effect on actual thermal profile. So it may restrict or define uniformity of thermal profile, but in general, package resistance has much more effect than substrate thickness. So later, later you can adjust it to, to what you need. No problem with this. This is just demonstration. You won't get like 20 degrees temperature increase because of this thickness set to 3 times less value. Unfortunately, effect of substrate thickness is pretty small. Especially when it is, yeah.
The next statement, set metal thermal conductivity 398. Is that the unit is, what is the unit on that?
Units are just standard units. I cannot tell it out of my head, but if you type set metal thermal conductivity -help, it will tell what the units are. So let me check. So we start InVar. I have built-in help system. If you do set metal thermal conductivity -help.
Oh, okay.
Yeah, so the units is in watts per meter by degrees Celsius.
That metal is metal 1 or metal 2?
So by default, it applies to all metals. Okay. This is like setting for all layers that have type-defined metal, and but there might be cases when you need to assign individual properties for individual layers. For example, your metal 1 is tungsten, and it would be different. So this, for more detailed assignment, we command set layer params. And this command you set thermal conductivity, thermal diffusivity, and can define thickness. For layers that are above substrate, you usually do not need to do this because thickness is part of ITF or IRCX file that you read in. But there are also substrate layers like diffusion layers, thermal isolation trenches filled with different material. So for these layers, you define thickness because this is not the part of ITF. There are no diffusion layers in ITF and RCX. So for you have ability to define thickness here.
It looks like the dash thermal conductivity arc still, because in the layer map, the OA material only metal. So if you have metal 1, metal 2, or metal 3, it will all become metal.
No. Please check what I highlight on the screen.
Okay.
The very first parameter is layer names list. So you can define single layer or a couple of layers or more layers that this parameter will be applied to.
Okay. Got it.
And actually, you can do it not only per metal layer. For example, in your ITF file, you may have several oxide layers between metal 1 and metal 2, and normally you have. So you can define, even for oxide layer, you can define oxide layer parameters.
Okay.
Yeah, I mean, that all makes sense. We got the diffusivity will give us the transient characteristics as well.
Yeah, but diffusivity doesn't make sense for static analysis, so that's rather transient analysis.
For what we're interested in, at least our immediate task at hand, that's some of the bulk material, and we really put in our D process. So there's a thermal barrier of the isolation layer would be possibly a valuable D for us to add and study.
Okay. Also, if you have like a thermal layer like across the whole die, and like for one of our customers, this is sapphire substrate. They go silicon on it, and they would like to assign different properties to sapphire substrate. So also can do this. So
good.
Okay. Then what's next? Let me see. This one is still running simulation. So what stage we are? So we are still running Spice Engine for this. While running, any other questions or what can answer you? But so ask. But I also have a question for you.
Go ahead.
What Silvaco tools you currently use? Do you have Hypix license?
Yes, we have Hypix.
Okay. So
we can generate DSPF.
Very good. And obviously then you have expert license.
Yes.
Okay, very good. So then you can have full use of it. Then, please.
I have a question on the Spice netlist. I think yesterday you showed us the Spice netlist. The model file shall use like vtl.inc file. Can we just use regular library file that XFAB provided?
So let me check. So and please repeat your question again. So let me go to Spice netlist. So what's exactly the question?
The model files here. Okay, so
xt06.lib, right?
Okay. So using the regular expression, because Shell was using some kind of underscore VTL.
And this is unfortunately I do not know, and I cannot give you advice because I do not know what really what. I just use data that I get from him, and I did not get into details.
Okay. Now, in this simulation, I set it up just to power up our our Doppler inverter to 6 volt, 6.4 minus 6, and reading not a stressed condition. I think the purpose is just to make a first run on InVar. Later, if I don't know if we have time, we could, we have this lightning stress condition where our output will see, perhaps 300 volt, 300 amps condition in a double exponential waveform.
So I guess you just provide different SpiceNet list, and then all the voltage definitions in Tickle script should be in sync with the SpiceNet list.
Okay.
So I do not see big problem here, because all goes in your hands, and what you only need to make sure that data is not contradictory between SpiceNet list, Tickle script, use proper libraries, and that's pretty much it.
Got it. Okay.
Also, please make sure in the original net list that Michelle gave me, there were quite complex subcircuits in the SPF net list. We required that everything would be extracted to the devices or device subcircuits. In his original net list, there were subcircuits including many devices, and these subcircuits were not annotated neither with the pin coordinates, neither with the own boundaries. So that required some rework. So let me show you what a good SPF. So what we had to redo. So all this parasitic component section is okay, but when it comes to the device section, the very bottom, come on, it's still reading it. Very slow. Now, if you don't mind, I will switch to different editor. This one has big, nice letters, but it's very slow. Okay, so this one is less legible, but okay. So the instance section. So see, all the subcircuits here are actually representation of devices. So these polyresistors or diodes. And the way I was checking what Michel was extracting, he was removing extraction of diodes in his configuration file. I do not know how it is correct, because in the next extraction diodes were back into the circuit. So again, this is what you need to decide, because these are like parasitic diodes as far as I understand. This is what you need to decide, because I don't know what your circuit is. And also we have seen here transistor subcircuits also. Let me check. Here XM. So subcircuits are representing actual devices. In his original extraction, it was like very big, like 100 component subcircuits were inserted into original extraction. So please, this happened probably because in Hypex settings, cells were not set to explode, and some cells were presented as H cells. So you understand what I'm talking about.
Kind of. Yun, do you have a question?
We have a choice of make explode or H cell.
Yeah.
Yeah,
So
well, extract many devices. That I don't know what he did, but really there's not.
Yeah, but I don't know. Sometimes transistor, if I don't explode it, upper, sometimes you cannot see the action. So upper connection, he exploded all the transistor level.
But for this extraction, for the second extraction, I checked the error messages of Hypex, and Hypex went out clean without any single warning. So this extraction is correct.
So you extracted without parasitic diode.
Without
parasitic diode.
No, I believe this one with the parasitic diodes, but I'm not an expert in Hypex. This is why I warn you that you need to check your extraction parameters. I do not know your technology. My goal was just to clean up the flow and make sure that your data runs smooth and there are no problems. Fine-tuning of extraction, fine-tuning of the spice net list. That's all your domain. Unfortunately, I do not have enough knowledge to do this.
Okay.
So let me close this. So what do we have? So it's still running. So also then, for this run, as you can see, I have two versions. First one is flow static and second one is flow transient. Again, what's the difference between static and transient run script-wise? So difference is really small. For run we add the word analysis type transient to set analysis options, and that's it. But the difference in the results is really important, because for static run, when you do analyze temperature, for example, you get saturated temperature. So tool calculates average power dissipation, and the temperature is temperature that or circuit will reach over the period of time. So it's not like this moment temperature. So let's if you dissipate 1 watt, then chip would heat up, and sometime, let's say in 10 minutes or in 1 hour, it will reach equilibrium temperature. So this is the temperature that we report in static run. Also for static run, we report average voltage drop. So you may have like voltage drop profile, But for static run, we calculate average, and we report just average. So you can easily overlook peaks in voltage drop. But this is static is pretty fast, and this is good estimate if your it has any severe airdrop problems. So the first step we have seen yesterday with the prime run, when we run without any circuit ready. So it was just very rough check. Then second level, this is static run that we do right now. And the type is transient run, where you see actual waveform profile, and you can detect peak voltages, and you can see your temperature increase in dynamics and very short period of time, though, because you won't run simulation for 15 minutes, I'm afraid. And also you can see power dissipation map, so you can estimate how uniform your power density is. Okay, and it looks like we are done with the static analysis. So if we start GU, and literally I did it before, and I see some artifacts that I cannot explain, and this is probably because I do not know the design really well, or I got some data that is not like your intended data. So because as the SpiceNet list was heavily edited. But let's start. Okay. And see the results. So I have pretty severe temperature deviation here in the report. So that means that the J parameter was really incorrect. Most likely, I know what it was. So probably Mel just took it from DFFRS design that is really small, and it shows abnormal temperature increase, absolutely abnormal. So when you get your data, please check what your package thermal resistance is and set correct number, because I do not know what it really should be. This is actually comes from a package supplier, so they give you package resistance numbers.
Say the JA units are watts per
watt per by degree Celsius. But this is standard, so this is in size system. Okay, so it's your design, and if we check maps, temperature obviously is way off. That's just unrealistic. Power. So for power, we see that for given pattern, for given waveform input, this is probably power off. Only in this area we have power dissipation, and that's for groups of transistors or transistor fingers.
Okay.
These are the areas of highest power dissipation. The rest of the circuit is pretty much quiet for given simulation settings.
Okay. Actually, not a big power dissipation, right? We're looking at the units are microwatts per micron square.
Yes. So we do report power dash summary. Report power dash. Then average power is actually it's pretty big. 53 watts. And it is reported by SPICE simulation.
The whole design.
This is whole design, but again, I'll say I'm not sure that SPICE netlist modifications were done correctly. Because if you run SPICE netlist alone, you would get the same 53 watts of total power. Maybe settings for inputs or something else was screwed up. So at this moment, I assume that input data may not be correct. And I hope you can check it and you can provide correct SPICE netlist with the correct DSPF.
Okay.
What power actually you expect from this simulation?
Not 53 watts. It looks like that's a Doppler area, and I think I'm not sure.
But not 53.
No, definitely not. I mean, if we just powered up in the D condition, it should consume maybe 40 or 50 milliamps over 12 volts. So I'd say less than 1 watt or close to 1 watt is what we expect.
Okay. Definitely somehow netlist or whatever in the SPICE data was screwed up. So I believe you can provide more correct data. Because it was heavily edited and I don't know who did this and what was done. I just used what I got.
That's why I was asking the question on the DSPF. I don't show thousands of transistors, and then he started at it. I mean, the skid is not that big. The multi-finger devices there. There's hundreds of them.
Yeah. So, excuse me, is it right here? Is it single transistor, multi-finger transistor for this one?
Yes.
So then each one was extracted as a separate transistor. That's what I can tell you.
Okay. So maybe that's why he sees hundreds, thousands of devices there. Then I can believe it.
So these structures, as far as I understand, are pre-resistors. There is some like chain structure that takes almost all the area.
Yeah.
Is pre-resistors?
Metal.
L resistor.
L. So it's like this also were extracted like separate devices. So you see, these are devices, and they just follow the shape of the metal routing. If we zoom in, these are all R devices. That's probably what count such a big
actual layout has just one piece of metal resistor, but the InVar simulation, David used me to cut the resistor, each piece of then you see the temperature in the certain area you'd like to see the temperature. So we divided the resistor into small pieces.
Right.
Okay. now with this such consumption reported by Spice Engine, and reason not to trust it, it's quite Spice Engine, so and certified many times, so what we get from this SpiceNet list. For this consumption, if it airdrop and let's metal 1, so actually only one area of extremely high airdrop, and of course with such unrealistic power consumption, airdrop is also getting out of bounds, and most of airdrop concentrated around this area, because this area has, it was it's one of GND. Yes, it was one of JB, I believe. No, I'm wrong. Oh, then GND. Yeah. This GND ground routing, and because of extremely high current consumption here and very narrow line connecting to this area, actually it goes not straight to the transistors as far as I understand, but it goes to the well.
It goes to the well.
And because of all these parasitic diodes that actually are extracted from the well structures, it shows extremely high current consumption that causes this extreme airdrop. Again, I do not trust these results. Circuit itself should verify that this is correct circuit. And this is 99% I am working with the wrong input data. But what is good, we cleaned up the flow, and the flow runs good with your input data. We created layer mapping files, and everything is in sync. So what you need to do now, you just need to correct Spice data for Spice netlist based analysis.
I have a question. You mentioned layer. You can define a N well or P well. So then, for the IR analysis, there is a current path going through substrate or N well. It would we have the ability to see it, right? I mean,
no. Unfortunately, no. For thermal purposes, you can define parameters, but for airdrop, you cannot operate with the substrate layers. You can do airdrop analysis only on metal and cut layers, and in some cases on poly layers, if you include poly layers, but not on diffusion layers. Diffusion layers are like continuous spaces, bulk material. So calculate airdrop graph in such distribution, this is beyond the capacity of the tool. We want well-defined geometries.
Okay. Oh, you mentioned poly. Is that including the gate poly?
Including any poly, but gate, how much current goes through the gate?
We will probably see in the transient, because gate would turn on with a fast pulse, maybe a nanoseconds, and it propagates. If you have a multi like this one, has a maybe correct me, maybe 150 micron or 200 micron long gate. So expect it might have some delay, on the far end of the gate to turn on.
You see, if you expect to see some delays, I would recommend you to use Spice simulation alone and use detailed extraction, non-reduced parasitic extraction for this. because what we do measure and we simulate airdrop on metal structures and via structures. Delays, I believe Spice Engine is the tool that should be used. We just reuse results of electrical analysis.
Okay. You're using Spice and process detail extraction. Is that
non-reduced parasitic extraction?
Non-reduced parasitic extraction. Okay.
So you see, I can show you what do I mean. So let me view parasitics. So if go to layout view, let me turn everything and preserve only metal one, metal L. Excuse me. So here we have a lot of reduced parasitics that do not really represent actual geometry. But if we go to metal 1, we see that on metal 1, action was done pretty accurate. So actually repeats structures, including the cuts in the metal routing that we have in metal 1. Let's do this one also and change color. So, yeah, so they cover pretty well all shapes. But if you do like reduced extraction, then and here these are transistors, I believe. So yeah, you can actual parasitic extraction goes. How well does it map to the actual layout?
So treating each finger as a separate NMOS.
Yes.
Yes. So in order to get what you were referring to in terms of the effect of the poly resistance and the, the involved in charging the poly from one end to the other end, you extract. So each finger has segments, sub-transistors in, be extracted to a finer resolution than.
Yeah,
reduced by finger. It'd be by finger and by segment within finger.
So as I'm trying to understand this green lines, see red is metal 1. Green is the
lines actually outlines of parasitic resistors from the SPF.
Okay. Okay, so now that one that has multiple resistors and uniform. I wonder. Contacts.
Yeah.
So these guys trapezoid shape. These are probably representing contacts. So you see, we do not show contacts to poly or contacts to diffusion, but these are still extracted as metal 1 resistors. So they actually go to diffusion, I guess, at these points. I just did not read metal to diffusion contacts, and I cannot display it here. But I believe you are right. This point where you have contacts to diffusion.
And not extract poly resistance, right? So that's why there's no poly layer shown to the right.
You see in the layer map there is no poly.
Right.
So in this the design itself has poly data. SPF has poly resistance data. We did not read layout on poly, and we do not display it because we skip poly layers on layer map, because we are looking for R drop on from metal 1 to metal L. Nevertheless, it's all included into simulation, into calculating currents, power, and such. So you are losing only visualization here. You, by the way, because original mapping file that I got from Michelle, it was including everything. It included diffusion layers and such, and then he reduced it to the minimal subset.
Okay. The reason he got rid of poly.
I asked him where it is expected to have airdrop, and came to the conclusion that poly here is like gates, and gate has small content, and mostly we should be concerned about metal layers. And it's also good to have only required subset of layers in layer map file, because the more layers you have, the more memory it takes, the more shapes you have to store, the time to process these shapes. So this is also a matter of performance. So storing more shapes, it comes at price.
Yes. So we are planning to have this one transistor, as design, the analysis design, not the whole chip, to see the transient gate effects.
Please tell me, who is supporting you now? So who? Yeah.
Nagat. I don't know his last name. His first name is Nagat. I guess Nagat Akapidi.
Naga.
Yeah, okay,
So
Naga.
is he from PDK group?
I'm not sure where he's from. He is replacing Michelle.
Because I know one Naga here in Santa Clara, but not aware of any Naga in Texas. But I just may not know all people there. That's possible.
Well, I don't think he's from Texas. I think he's somewhere in California.
Then I will ask him.
I've looked up his name. It's Naga, Akkapedi.
I cannot read it. Sorry. That's bad with the spelling. But
Okay,
Naga, I will
ask
ask him. I will ask him.
He is a guy you know.
Okay.
But I mean, our approach will work, right? If we just segregate this single multi-finger power device and run the extract of unreduced DSPF and.
Yes, this is the recommended way.
Okay.
That's pretty much what I was going to show you today. I believe you will get all the data to reproduce it on your side, but please request, and do you have Smart Spice installed?
Yes, we do.
Okay, so please request latest Smart Spice, and request also Hypex, because Hypex had many improvements, and right now the good version to use, let me show you. So the good version to use for Hypex is 3.50. No, let's check. Hypex minus VS. This is our internal stuff, yes. So the good version to use is 350.38. The only problem, this is development version. This is really good version. But probably we'll have to create like a B or C version for you because we do not release A to the customers. For expert, you are good to use whatever you have. For Smart Spice, I'm afraid you may need again Smart Spice minus VBS. Smart Spice you may need this version 427.3a.
Okay.
So why is it so? Because you have some devices that we did not support in the parsing and use Spice parser. And Smart Spice implemented support for parsing for not for themselves. For themselves they are good for a long time. For forever. But they do also parsing for us. They prepare netlist data for InVar, and they included support for several devices, not only for you, for other customers also, in this version 427.3a. So you may somehow request this version as well, but they have to convert it to B or to C version. This is what I would like to say about versions. So one is really good to have. It provides much better, like what I see. And this one is required for correct parsing of your input data. So that's pretty much it.
About version, do they have a new version?
We have a recent version, and for minus yes. So we have this 1.11.1c. So this is ready to be released to the customer, and Peter should have link to this version, so he can provide you download link for this.
Okay.
Because the versions, our IT team it automatically places on the web for the customer download, so it should be available.
Okay. Perfect.
So how I can help you today?
Any more question? Do you guys have any other question? Tom, Barb, Yun?
I do not.
Okay, so I think I get the drift of it. I have the primary setup file to move forward with.
So I will provide these files to Peter, and he will then handle interaction with the customer. I just do not want to interfere with the field offices, so that's like the domain, and I don't want to get in.
Do you know where Michelle moved to, or he still in San Diego?
Also, what I do not know. Probably he has his LinkedIn profile updated, or will update it in time then. But I really do not know.
We have worked with him for many years, and so him.
But then probably he can stay in touch with you.
It's potentially a very powerful tool for some of the that we have. So if we can.
Excuse me, the question, where are you located? In what place? I didn't check your website yet.
Located in Arizona.
Uh-huh.
Although Bob Berger on the line is actually in North Dakota.
You are distributed.
Has a remote office, and we have a couple of offices in Arizona. So David at one, and I'm at another one.
Okay. And designs do you do per year?
Few. Get out 4 designs per year. That's a good year.
This is XFAB technology. Okay.
Yeah.
Okay. It was really good to talk to you. I appreciate your patience with me and my explanation. So, if you have more questions and there's nobody to support you in this area and answer, so call it and we will try the answer or find the right support person for you.
Okay, thank you so much.
Very good.
Thank you.
Right, you have a good day.
Bye-bye.
Bye.
Bye.
Bye. Bob?
Left the meeting.
Cool.
Yeah. I think that is what exactly what
Left the meeting.
we're looking for.
Yeah, too bad it doesn't work the substrate current problem.
No.
That was a good question. That would be another tool.
Although he mentioned he has a customer who built a device on Sapphire. So I think so for DI process, right? For example.
Yeah, like you could add the the layer and account for the thermal.
Yeah. So the substrate is So the substrate is now oxide, and and make or make the bulk and diffusion, make them look like a resistor. So I'm sure.
I mean, he was describing the model, right? Or the engine. So that's where the layer structures come. But in terms of IR drop, that's a different thing. The substrate would look like a single resistor. It's not bounded like metal or poly. So you can see it's a different problem. How do you get it out?
Mm-hmm.
You know where all the current's going to be ejected before you can mesh it.
Right. Okay. Well, once I get his file and update the software, we can.
Yeah. So what I didn't know is if he had started the simulation before we started, or did he start it and it was just that few minutes?
I think he started, in the session.
Okay. So that'll be fast. Although long answer, maybe it was fast because the data.
This is
yeah. So
rough.
I didn't understand all the manual editing. You know, he's talking about the circuits. Is that do you think that's the device sub-circuits that had to be?
There's a explore mode where you can open up the circuit and get connection, and then there will be the netlist where those are sub-circuit transistors. Otherwise, they would, refer to a library or something.
So is this basically making it
instead of a hierarchy?
Okay. So then every instance of circuit gets expanded.
Right.
List. Okay.
Right. I don't know what Michelle did to manipulate the circuit. I mean the parasitic.
Right.
But we have to re-extract it. But I don't think we are going to run whole chip. So we probably have just TVS and receive separate from the chip, and then run the thermal and power device.
Likewise, if you want to study the layout of the modules, then you construct something just for that.
Right.
But I think I maybe agreed that there's options in how you extract the to resolve it not just by finger, but cement the fingers. And using, really just do the spice simulation to get the timing. You don't need the thermal.
Well, I'm hoping I can see it graphically.
Yeah. I mean, you could probably visually see the extraction in VAR.
Right. With spice, you see it. You have to
use that list.